all the information that I'm going to present is publicly available, be that through Wikipedia or anywhere else. So I've gone to great lengths to make sure that I don't share anything with you that I'm not supposed to for commercial reasons or for legal or regulatory reasons. And lastly, I'm going to talk about future nuclear technologies, and you might decide to make investment decisions based on what we discuss in here, but I am not a financial advisor. Please don't sue me when you eventually lose money on NuScale. Okay, that shit out of the way. I would like to basically start by teaching you guys the basics around reactor physics. This is pitched at an A-level kind of level, I guess, but you know, we'll start with sort of radioactivity. A lot of elements are, or pretty much all the elements that we're generally exposed to that we come across are stable and are quite happy to exist with the number of subatomic particles and bits and pieces that they have. But some of them are also unstable. The forces present inside them aren't balanced in such a way that the atom can maintain its structure, and it will attempt to correct that by reorganizing itself internally. What I've got here on the slide is an atom of uranium 235, and just, you know, the center is a highly compact collection of subatomic particles called protons and neutrons. Protons have a positive charge. Neutrons have no charge. They both have a roughly equal mass. And then around the outside, we've got electrons, which do not orbit atoms. Although they're drawn as orbiting atoms, they actually occupy quite complex quantum distribution functions that are only really important if you're into that sort of thing, either because you're doing particle physics or because you're doing electronics. When you see elements written down, you tend to see them written in the form of one or more letters that represents the element, a mass number, which is the sum of the protons and the neutrons, and an atomic number, which is the quantity of protons. So to get the number of neutrons, which is important for what we're about to talk about in relation to isotopes, you would subtract the atomic number from the mass number. The atomic number is important because it generally governs the chemical properties of the element. Isotopes, so an isotope is an atom that is the same as, or an element that's the same but has a different number of neutrons in it. So you could have two atoms with the same chemical properties, labeled as being the same element, but they might have a different weight because they vary by 1 or 2 neutrons, but they behave in exactly the same way in chemistry. So they're referred to as being isotopes of each other. So isotopes will have a different mass number, but will have the same atomic number. So we said about some of these atoms being unstable, and they reorganize themselves internally to try and become more stable. And they do that through radiating. They do their internal movements, and as a result of that, they then release a different one of 3 principal types of radiation, alpha, beta, and gamma, which you'll probably remember from school. An alpha particle being the nucleus of a helium atom. So it's 2 protons, 2 neutrons, carrying a positive charge of 2. So it's got a mass of 4 and a charge of 2. And we write this down in the form of an equation where we start with a element. We show it's the process of alpha decay, which then gives us a new element. In this instance, it's thorium 231. Thorium has an atomic number of 90, plus this. Oh, my finger runs out there. Oh well. Plus this helium ion. And you'll see this with beta and gamma and so forth as the mode of radioactive decay. These are all supposed to be animated, but I couldn't get OBS and animated stuff to work. So I said that some elements are stable and some are unstable. What this graph shows is the number of neutrons versus the number of protons in a given nucleus of an element, and there's this black line through the middle which are all stable. This is really hard. How do weather presenters do this? This is really stable right through the middle, where all the stable elements live. And basically, if there's an imbalance between the number of protons and the number of neutrons that take it above or below that line, it becomes unstable. The heavy elements are all sort of up this top corner where the black line doesn't really exist. So uranium lives over here. Yes, because it's got more neutrons than protons, I think. No, it's got more protons than neutrons. Sorry, so it lives above the line, but this direction where the black line runs out. The blue means that those elements try and become stable through beta decay. Pardon me. Fizzy beer was not a good idea. So they give off electrons to become more stable. So a proton inside the nucleus splits and becomes a neutron splits, becomes a proton and an electron, and the electron nubs off, and the proton then stays in the nucleus, and then alpha emission is sort of yes. I don't understand that bit perfectly, but yeah, essentially some do one, some do the other. This sort of splitting can also be triggered. So at the start we had this our uranium-235 atom, and it's got a relatively long half-life, but if we add another neutron to it, it becomes uranium-236, which has a very, very, very short half-life and immediately decays into two elements. Typically, most of the time it decays into barium, 141, and krypton-92, and it does this pretty much instantly. So you add a neutron and it splits, and this is referred to as fission, and it gives off 3 more neutrons. Uranium, though, has although in this picture we've got 3 neutrons being given off, that only happens 85% of the time. 15% of the time, at the bottom, the uranium will capture that neutron and become uranium-236, and doesn't do anything. So because of that 15%, the average number of neutrons being released due to a fission reaction from uranium is actually 2.4. I think it's 2.4, 2.4. Which sort of, I don't know, I kind of like the way that lines up with the average number of children in a nuclear family being 2.4 as well. So in this term here, at the end, we've got this 166 MeV. MeV means mega electron volts, so millions of electron volts. And an electron volt is a convenient unit of energy for subatomic physics. It is equal to 1.9 times 10 to the minus 16 joules. So it's a very small amount of energy, but it's measurable. And the question is, where does that energy come from? Where does it come about? And it's to do with the amount of energy that is bound up in the structure of the nucleus of the atom. And you can think of this as a bit like a gravity well. So it's negative energy because it's a binding energy, and heavy elements, or sorry. There's a point at which there's like a minimum amount of binding energy, and it's on iron at the bottom. So if your element is lighter than iron, if you were to split it apart, you have to put more energy in than you get out. If it's the other side of iron, heavier than iron, you get more energy out of splitting it than you put in. And converse is also true in fusion. So anything that you join together to the left of iron, you get energy out from fusing it, and you put energy into fusing it if it's to the right of iron. what this means is that through radioactive decay and normal processes, because the second law of thermodynamics applies to this, is that everything tends to become iron over time in the universe, except when you have a lot of energy. And then when you have a lot of energy, you can create these heavier elements. So these are so they are, the theory is that these are all created during things like supernova events, where there's huge amounts of energy and huge amounts of pressure surplus that can be used to create elements through an endothermic energy absorbing process. So stars, when they're operating normally, turn these lighter elements into heavier elements. So they burn all the helium, then they'll start to burn hydrogen. Sorry, they burn all the hydrogen, and they'll start to burn helium, and then they'll start to move through these heavier elements, fusing them until they basically run out of fuel and becomes very dense iron balls down here, or they explode. And if they explode, then when they go supernova, they can create these heavier elements. So that energy, sorry, which is where we were starting with this. Krypton-92 and barium-141 have binding energies of 782 and 1,170 megaelectron volts, respectively. When you put them together, when you split a uranium atom with a binding energy of 1,786, you can add all these bits up. So you take a negative number, add another negative number, and add another negative number to it, and you get 166 as the sum. And that 166 megaelectron volts equates to roughly 2.7 times 10 to the minus 17 joules. And if you've got a big enough reactor like an EPR, like the ones that they're building at Hinkley Point C, typically you have somewhere around 1.7 times 10 to the 26 fission events per second, which gives you a nice 4.5 gigawatts that you can use to generate heat and eventually steam and stuff with. So even though it's a small amount of energy, because the number of fission events going on inside the reactor core is so high, you get a useful amount of energy out of it. There is a gotcha in all of this, which is that, so I briefly mentioned that there are forces at play inside the atom. There's a strong nuclear force that holds the nucleus of the atom together. So you've got all these protons and neutrons sort of stuck together, but the protons are very positively charged, and they want to fly apart from each other because positive charges, same charges repel. So there's a strong nuclear force that holds the whole thing together, but there's also a weak nuclear force that repels stuff that is going into the nucleus. So when you throw a neutron at it, you need to A, get close enough that it will get captured, and B, be traveling at just the right speed. If you're going too quickly, you'll bounce off. If you're going too slowly, you won't get close enough. So it matters how fast the neutrons are going. So going back to creating neutrons in a fission reaction, it matters how quickly these ones are traveling for them to be subsequently captured by the next uranium nucleus in order to generate to cause a fission event that generates more energy. So this red curve represents the sort of spread of velocities that neutrons are created during a fission event, and they come out at about 140 kilometers per second-ish. And to actually make them useful, we need to get them down to 2 kilometers per second. And neutrons don't have a charge, but they do have mass, so they don't interact with magnetic or electric fields. Literally, the only way that you can slow them down is to get them to interact physically with other nuclei in order for them to hit them and bounce off. So you're trying to transfer momentum away. And you get your best momentum transfer when the mass of the object that you're hitting is close to the mass of the traveling object. If they're exactly the same, then you lose half your momentum in each collision, which gets you down here quickly. So things that make good materials for that purpose are referred to as neutron moderators, because they moderate the energy of the neutron, and they are the good ones have an atomic weight that's close to 1. So hydrogen is very good, but hydrogen has another trick up its sleeve, which we'll talk about when we get to sort of reactor construction. Let's select the right thing. So the basics of a reactor, they consist of some form of nuclear fuel, which will contain uranium, typically as an oxide or a ceramic, or it might be metal uranium for very high power density reactors. That is sat in a big tank of water or some other coolant that you use to take heat away from your reactor core, because the energy that you're generating comes out as heat. So you take that, send it to some kind of heat exchanger. If it's a thermal plant, which we're talking about, then you'll be trying to generate steam so that you can use that in turbines. And that's sort of your coolant job, is just to continuously take heat away. You want to be able to control the speed of your reaction. So if you were to allow this reaction to just continue unchecked, because there's always 2.4 more fission events in each generation, it grows exponentially, which is, this is one of the things that sort of amused me about not amused me, but I found interesting about the current coronavirus thing, is that I instinctively understood the R number, because it's effectively exactly the same as the reactivity measurement that we use for measuring how the reactivity of a nuclear reactor core. So it also uses an R number. If R is 1, the reactor is critical and is producing the same number of neutrons or same number of fission events in each subsequent generation as they are in the current generation. So you have a consistent amount of energy coming out of your system. If it is above 1, it's referred to as supercritical. So the reaction rate is growing. There's more fission events per second or per generation. And if it's below 1, it's subcritical. So the reaction rate is tailing off. To control that, reactors use materials that absorb neutrons. So I said that hydrogen's got this nasty little trick. If you throw a neutron at a hydrogen atom, instead of it bouncing off and slowing down, what happens is it gets captured by the hydrogen nucleus and makes deuterium. So you end up with a hydrogen atom with a nuclear weight of 2. So what you do to reduce your neutron population inside the reactor core is introduce materials that have this property of absorbing neutrons without contributing further neutrons to the nuclear chain reaction. So these are materials typically like hafnium is quite a common one for a control rod. And they're just neutron absorbers, basically. They're greedy. They soak up all the neutrons so that you don't have enough to continue a exponential chain reaction. And generally they're used, you just pull them in and out. It's really agricultural, but they just slide them in and out. Most reactors will have, or all power producing reactors will have some kind of biological shield, and that is to protect people outside of the reactor from the radiation that's being generated inside. Beta radiation, which is electrons, will be stopped by a sheet of paper. They're not particularly lively. Alpha particles similarly. So the steel containment or whatever you've put your reactor core in will contain beta radiation and alpha radiation quite effectively. Gamma is much more spicy. It's got much more energy and exists as an electromagnetic wave. And to stop that stuff, you need things like lead shielding. the big problem isn't the alpha, beta, or gamma radiation, it's the neutrons. So most of what the reactor technicians refer to it as is shine. Most of the shine that you get off the reactor is these neutrons that come flying out, and they will activate materials around them. So you've got anything else in the surrounding area that's capable of capturing neutrons. The elements inside that will capture neutrons, become new isotopes, and some of those isotopes will be radioactive. Gold, for example, has a very radioactive isotope. And one of my colleagues managed to lose a watch that had gold plating in a reactor compartment, and by the time we got it back, it was very, very spicy indeed. So it exists hanging on a string at work as a warning to all others not to lose gold crap in a reactor compartment. You might also have a moderator. So we talked about moderating materials, and this is to do with this idea of neutron economy. So reactors have different levels of performance in relation to how well they use neutrons that are produced during the reaction. A lot of them will escape. Some of them will be used to continue the nuclear chain reaction. You can improve your odds of a neutron causing a fission event by having a moderator, and you can reduce the amount of neutrons that escape using a neutron reflector. Beryllium's quite a common one. So if any of you have read about the Demon Core experiment, slotting experiment, where he's had a big ball of plutonium and 2 beryllium hemispheres and a screwdriver, the beryllium was affecting the critical mass of the plutonium. So less material was required for it to go critical because the neutrons that would be escaping were being bounced and were coming back in. And also your choice of coolant is important. If you were to use plain water, the hydrogen in normal water will absorb neutrons. But if you use heavy water that's made with deuterium, the hydrogen doesn't absorb neutrons, so you have more neutrons available to keep your reaction going. And this is important because uranium, when you dig it out of the ground, is about 0.7% uranium-235, which is useful as reactor fuel, and 99.3% uranium-238, which is not as useful. So your neutron economy in your reactor really defines whether you can burn natural uranium or whether you have to enrich your uranium. So a few different reactor designs. These ones are natural uranium fueled. This is one of the 2 nuclear reactors that were constructed on the northwest coast of England. Probably the first sort of major operating reactors in the UK, and their purpose was to make plutonium for the nuclear weapons program. Plutonium as a bomb fuel it's broadly similar to uranium, except that it has different chemical properties to uranium. So if you want to make a bomb out of uranium, you need to enrich it a lot. And you want to get your percentage of uranium-235 from 0.7% up to in the region of 80%. And that requires a lot of energy and big facilities and so forth. It's very difficult to do because the uranium-238 is chemically exactly the same as the uranium-235, so you can't separate it chemically. Plutonium, which you can make inside a reactor, has similar nucleonic properties, except that it is chemically different to uranium. So it allows you to use a chemical separation process. So you convert uranium-238 into plutonium in a reactor, and then you can chemically separate it from the remaining uranium in your spent fuel, which is what these piles were used to produce. And they were air-cooled. So air was being blown through the reactor core and out a chimney by there to cool them down. Very first gas-cooled reactor, I guess. Which brings us on to gas cooled, where you have a coolant gas that circulates through your reactor core. Carbon dioxide and carbon in general has a very low probability of capturing neutrons, so it's makes a good coolant and makes a good moderator, because it's got a relatively low atomic weight, and it's also doesn't collect neutrons. It doesn't capture neutrons very easily, which lends itself to being a good moderator. Magnox was the first generation of power producing reactors in the UK. So they had fuel inside them and inside a large graphite block, effectively, and carbon dioxide was pumped through to cool them down, and that carbon dioxide was used to generate steam. The power stations that we had at the time all burned coal, so the idea was to have something that produced steam at a similar temperature to a thermal coal-fired power station. We also didn't have the ability to make very large steel pressure vessels, so this thing runs at a pressure of 40 bars, 40 atmospheres. AGR was a development from that advanced gas-cooled reactor, brought the steam generators inside, continued to use carbon dioxide. This is the backbone of the British nuclear fleet. So it's very different to what you find in the US, because we don't use water, we use carbon dioxide to cool them. They have some problems with the carbon cores, the graphite inside. Neutrons, when they smash into crystalline carbon, displace some of the atoms inside the carbon lattice, because it's a crystal, and those displaced atoms have an energy associated with them, and this energy builds up over time, and the displacements in the matrix can cause brittle embrittlement and fractures to form in the carbon, and so on and so forth. So there's a big problem with the carbon cores inside these reactors cracking and breaking, and although that doesn't stop them from being good moderators, it does affect the mechanical properties of the core, so materials don't slide in and out as easily, because the hole that they go down is now all crooked and knackered, and that's bad, because if you needed to shove a control rod in there quickly, it might jam. So these reactors have a very limited life, which we've extended many, many times. And then heavy water. Mentioned how deuterium has a low capture thing. This was a Canadian design that, instead of using graphite, used heavy water in exactly the same sort of way of using a graphite core in the AGR reactor. So it provides moderation, but the coolant is water. To stop it for the coolant from boiling inside the reactor, it's pressurized. But again, the Canadians couldn't build these huge pressure vessels. So they have pressurized tubes that run through the reactor, because tubing is easy to make. And the reactor vessel itself isn't pressurized. I'm going to skip the slide on enrichment. Boiling water reactors, same principle, carbon core inside, except now we're using water for our coolant, and we allow the water to boil inside the reactor vessel, and the steam is used directly to drive a turbine. I don't particularly like these designs, because I feel like a two-loop design gives you more safety, but apparently because they're so basic and simple, it makes them more reliable. The AP1000 design that was licensed to be built in the UK used this particular style of reactor. The variation to that is a pressurized water reactor, where instead of allowing the water to boil inside the reactor vessel, you send it to a steam generator. PWRs have a couple of issues. One is that they operate at very, very high pressures. The reactor vessel is pressurized in the region of 200 atmospheres. And if it loses that pressure, then it can boil the coolant inside and expose the core, which is what happened in the 3 Mile Island accident. And you need that coolant to continue to remove heat from your reactor. Also, the steam that you get out isn't particularly hot or dry. So the turbines have to be designed to cope with wet steam, and the efficiency isn't as high as burning coal. So for each watt of thermal energy you get from a reactor core, from a PWR, you don't get as much, or a boiling water reactor, you don't get as much electrical energy out. And then lastly, molten salts. Molten salt reactors are interesting because they turn the entire concept on its head. Instead of having fuel that is stationary within the reactor core and running water through it as a coolant, what a molten salt reactor does is the fuel is actually the molten salt that's also the coolant. So it's only critical, it's only producing power when it's inside the core. It gets passed through a graphite moderator, which makes it critical. It gets hot due to nuclear reactions. It then leaves the core. So without the carbon, then it's no longer critical, becomes subcritical. The reactions stop, and then it travels through a heat exchanger, giving up its thermal energy to create steam, and then goes back into the reactor. So this uses the fuel as a coolant, which is really cool. In order to refuel these, though, they have to effectively reprocess the fuel on a continual basis. So molten salt reactors have this reprocessing module associated with them. But this is sort of, there's only been one working example of a molten salt reactor, and that was in the US. I'm doing terribly for time. Who wants to hear about a really awful thing that happened in the northwest of England? Everyone, good. So in 1950, I mentioned about these plutonium producing piles. These were built in October 1950 to produce plutonium for the British bomb project. And they discovered this problem with the graphite inside, where the neutrons would displace atoms in the matrix, in the lattice, and those dislocations had this energy associated with them. So there's this energy being stored in the carbon inside the reactor core. And what could happen was that it would build up, and then it would suddenly release all this stored energy in one go, and the reactor core would get hotter in really disorganized, anomalous ways, and that could cause bad things to happen to the reactor. So to fix that, what they did was they would heat the graphite above 250 degrees Celsius, and that would then trigger this lattice reorganization process. And it's similar to annealing metal, and they used to actually call it annealing, or a Wingner release, but effectively they're annealing the graphite to make it plastic again. And that was fine, and they were quite happy producing plutonium. And then the Americans exploded a hydrogen bomb, and in order to sort of keep up, the Brits, we wanted to build our own hydrogen bomb. And the thing that you need for hydrogen bombs is tritium, and lots of it. And you make tritium primarily by using lithium. So lithium becomes tritium and a alpha particle when you throw a neutron into it. It's the most efficient way of doing it. So you're converting a flammable metal into helium and tritium inside a reactor that's built out of graphite. To make this work, they actually had to modify the fuel and isotope cartridges to make the reactor run hotter, and they did that by removing some of the cooling fins on each of the fuel and isotope cartridges, so that they weren't as efficient as at transferring heat to the air. And these cartridges were made out of aluminium, and they literally just went and cut fins off them using a jig. So there's all this going on. We've got our graphite core that's filled with uranium, plutonium, lithium, and other bits and bobs. And on the 7th of October in 57, it was chugging along, and they noticed that some of the temperatures from the thermocouples inside the reactor weren't quite right. So they decided to do this nuclear annealing process, this finger release. And they did that, and the reactor heated up, cooled down a bit, but continued to be hot in channel 2053. So the operators at the time assumed incorrectly that the heat in channel 2053 was due to not all of the energy from the Vinger thing being released fully. So they ordered a second Vinger release, and then things started to get really weird because temperatures weren't just high, they started to rise inside the reactor. It took 2 days of this weird behavior before they discovered that it was actually on fire. The plant foreman at the time decided that this was just a bit too weird and he was going to have a proper look. So he removed one of the inspection plugs on the charge face and looked inside and discovered that their reactor was on fire. It had been for the best part of 2 days. So we've got these metals on fire inside a graphite core that's being cooled with air that contains lots of oxygen. So they decide that the first thing they're going to try to put the fire out is to blow more air through it to cool it down. So we're going to slow this fire down by adding more oxygen. That doesn't work. They've got lots of carbon dioxide on site because they've got a Magnox reactor being built next door. So they try the carbon dioxide, but they can't get enough carbon dioxide into the reactor fast enough. And so they're then worrying about, should we add water? Because if the water could do two things. One is it's going to act as a moderator. So it's going to increase the reactivity inside the reactor that they've just managed to shut down. And the other issue is that the reactor is burning hot enough that it can strip oxygen out of the water to feed the fire, and the remaining hydrogen then collects inside the reactor and can then cause an explosion. But eventually they decide to use water, and that helps, but it still doesn't put the fire out. And the last thing that they try is to shut down the ventilation, to shut down the cooling to the reactor core. And that, in combination with the water, finally puts the fire out a day later on the 11th of October. The extent of the fire inside the reactor is this fire affected zone. So this orangey bit here. So it started towards the back of the reactor, kind of in the worst place possible, pretty much. That's one of to get the water into the reactor, they were using scaffolding poles. So they put they cut the end off the firefighting hose and put it on a scaffolding pole and clamped that on and then jammed it into the reactor as deeply as they could. And a lot of them just got stuck inside. This is one of the fuel cartridges that's been completely destroyed. You can see the yellow there is uranium oxide, and a lot of the material that's left in here is aluminium oxide. So the cartridge is made out of fuel. It's completely oxidized and gone. That's one where you can still see some of the fins on it and how it's been damaged. I think this was one of the ones that they hit with a pole and it bent the fins. And that's pretty much what the cartridges looked like when they were whole, when they were manufactured. So inside is your uranium fuel and your lithium that you're making into tritium. So what happened? The official reports of the accident said that the second Vinger release caused the fire, and they blamed the poor judgment of the operators for performing the second Vinger release, and said that it shouldn't have been done, and that's what caused the fire. It was a human error. Da, 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 da. Anyone who studied accidents will understand that a human error is a symptom. It's never an underlying cause of an accident. It's very rarely an underlying cause. It's usually always a symptom of something else. At the time, the behavior of nuclear graphite wasn't well understood. The nuclear piles at Windscale were copies of the X-10 reactors that the Americans had been using to manufacture plutonium. But because of the way that the Americans and the British parted on the Manhattan Project, the Brits didn't we didn't have access to all the information about how the reactor performed, and we didn't really understand what the graphite was doing, which meant that the way that we were dealing with this finger issue was flawed, and the reactor wasn't designed in a way that it was designed in a way that allowed it to build up. And had we known more, we might have done it differently. And then there was the modification to the reactor, so introducing new materials that the reactor wasn't designed to be used with, and modifying the cartridges to make them hotter. And the last bit is always the bit that sort of gets me, is like, so we're heating combustible materials in an atmosphere that supports combustion, and it caught fire and everyone's surprised. There's a legacy from Windscale as well. This is in the UK, to license a nuclear reactor, there are 28 license conditions. So these are the non-negotiable rules that the regulator puts in place and says you must do this, that, and the other if you want to operate a reactor. And license condition 22, the licensee shall make and implement adequate arrangements to control any modification or experiment carried out on any part of the existing plant process which may affect safety. So what we understand now is that the underlying issue in relation to the Windscale Fire was this modification to the reactor, making it run hotter with exotic materials that it wasn't designed to cope with. So now we have this rule that you can't make a modification until it's been authorised by the nuclear regulator, and to do that you have to provide safety justifications and so forth, which is good. License condition 22 is also informed by the Chernobyl experiment that led to the accident, so it covers modification and experiments. Right, I am way over time. Small modular reactors, very quickly, are reactors that are typically 300 megawatts electrical output. They're modular, they're manufactured off-site. The idea by manufacturing them off-site is that you have this shorter build time because you turn up with finished modules that you just bolt together instead of building all these systems on-site and integrating them on-site. They're less expensive to build than a large plant, but the cost per megawatt hour, the cost per megawatt hour of energy produced is higher. I've said overnight cost here. So an overnight cost in nuclear industry terms is this is the book cost of producing the plant, not including any finance costs. So on paper, a large plant is more economically viable because the amount that you pay per megawatt hour is lower, but it doesn't take into account the fact that it takes a lot longer to build a big plant. Therefore, you have to borrow money for a longer time to build your plant before you start making money back from generating electricity. And there's also more chance for loss of political will and so forth that affects the building of your plant. So there's more financial risk. And effectively what that means is that you're spending more on interest on money that you borrow because of the increased level of risk, and you're borrowing that money for a longer time. And that then makes it more expensive to build a large plant per megawatt hour than it is to build a smaller plant, which means that small modular reactors, the cost of finance associated with them is cheaper per megawatt hour than the big plants. Sort of economies of scale not working, basically. This is the UK small modular reactor, which is being developed by Rolls-Royce and a consortium of other companies. I think it looks like a woodlouse, personally. It just needs a couple of antennae on the front by here. Yeah. It is not really small. It's much more power than what is considered to be a small modular reactor, but it is fully modular. The idea being that all the components associated with it are road transportable. Everything is manufactured off-site and integrated into modules where it can be. So imagine 40-foot ISO containers, basically, kind of size, and they're all just brought to site, bolted together, and then this roof is put over the whole thing. to make it look pretty. It's a 3-loop plant. Most reactor plants are either 2 or 4 loops. We've decided to do 3, just because it's different. There was some analysis behind that decision. And it's laid out in this sort of way. So reactors, turbine housing, and then water. The NuScale concept is very different. So they've come up with a reactor that is entirely road transportable, but it doesn't have a very high output at all because it's so small. So to get a useful output from the power station, the idea is that you have a bunch of these operating together, and you basically parallel them up to get higher output. But because they're so small, you can operate them in a pool, which improves the safety performance. So you cover everything with water, and that keeps all your neutrons inside, which is nice because neutrons are bad. The reactor itself is just this tiny bit at the bottom of the power module. The rest of the space is associated with generating steam, basically, and maintaining pressure inside the reactor pressure vessel. So it is a pressurized water reactor. So it's got a pressurizer to maintain pressure and stop the water from boiling off inside the core. And it contains the steam generator inside. It's very similar to something that was developed by Rolls-Royce back in the 1960s, called the Safe Integral Reactor. So SIR has this reactor core at the bottom, steam generators at the top, pressurizer in the top, very similar to the NuScale module, but the SIR was a lot bigger. Terrestrial Energy producing this molten salt reactor with a liquid fuel salt that goes through a graphite core. That then goes into a heat exchanger at the top, which is used to heat a different salt that doesn't contain fuel. And that salt goes to a secondary heat exchanger where it is used to produce steam. And the steam then is used to generate power, or the other one that they want to do is store hot liquid salt and then release it later to generate steam. So it's like making a big thermos of tea that you're going to enjoy later. So they can have a lower output from their reactor core, store hot salt in an insulated container, and then tap it later to make steam for power generation. So they're able to follow the load of the grid more closely with this reservoir of hot salt. And they also have the prospect of using heat from this to power other processes. But the main sort of beauty of this is the salt comes out at about 600 degrees, which is very efficient for power generation. And that's it. 20 minutes over. We did some basic nuclear physics and some reactor design around natural uranium and enriched uranium types. We did some stuff on molten salt reactors, the Windscale Fire, and I introduced you to small modular reactors. And any other beer. And I appear to have gone very pink, which I assure you is entirely a feature of the light.